Welcome to the webinar on the 2024 IRC provisions for prescriptive wall bracing. My name is Shane Nellis. I'm a previous building official in Washington State and work for the American Wood Council as the Pacific Northwest Regional Manager. This is part one of a four-part series, and in this part we'll focus on loads and connections and how they are important to the proper application of the IRC provisions and the proper design and construction of buildings within the scope of the IRC. The 2024 International Residential Code, hereafter referred to as the IRC, provides provisions for constructing 1- and 2-family dwellings, as well as townhouses, up to 3 stories above grade plane. The IRC is generally considered a cookbook for building homes and is predominantly a prescriptive document, meaning rather than giving general requirements for what is to be achieved, it provides specific methods to meet the requirements and thereby to construct a structurally sound building. Here are some of our main learning objectives. As mentioned, we'll explore the types of loads for buildings and identify gravity and lateral loads. We'll also determine what loads apply in specific regions and sites. We're going to trace those loads through the building and ultimately to the earth. And then we're going to make the connection. We're going to examine different connections for wall bracing. It is critical to make sure that it's attached to the structure above and below. And then we're going to understand the limitations of the code. And then we're going to also explore what do you do when you exceed those limitations. I mentioned the IRC is applicable to 1- and 2-family dwellings and townhouses not more than 3 stories above grade plane. This is outlined in the scope of the code, which is IRC section R101.2. Whenever applying the code, it is important to double check that the building in question falls under the scope of the code. For instance, if the building is greater than 3 stories above grade plane, the IRC cannot be used, and rather the International Building Code, or IBC, would be applicable. Now that we've determined that the IRC is limited to 3 stories above grade plane, we must understand what's considered to be a story above grade plane. Defined terms are italicized in the code, and their definitions can be found in Chapter 2. The IRC defines story above grade plane as any story having its finished floor surface entirely above grade plane, or in which the finished surface of the floor above is either of the following: 6 feet above grade plane, or more than 12 feet above the finished ground level at any point. Now we must also understand what grade plane is, which is also defined. And it's defined as a reference plane representing the average of the finished ground level adjoining the building. And it's important to understand that because the code actually requires the ground to slope away, that when you're determining that reference plane, it's established by the lowest points between the building and the lot line, but you're not required to take those points more than 6 feet around the building. So if that distance to the lot line does exceed 6 feet, you stop at 6 feet and just measure the lowest points within it. Another important thing to understand when determining the number of stories above grade plane is that within the code, there's an allowance for habitable attics that are within the roof assembly and limited in size to not be considered a story. If it is not a story, then the wall bracing provisions do not apply to it, and the stories below will not have to account for more wall bracing based on the habitable attic being above it. Here's an example of a habitable attic. This would not be considered a story per the IRC because the roof structure also transfers lateral loads to the story below, so there is no need to provide brace wall panels for the habitable attic. We discussed that townhouses that are 3 stories or less above grade plane also fall under the scope of the IRC. A townhouse, as defined by the IRC, is a building that contains 3 or more attached townhouse units. Townhouse unit is also defined, which is a single-family dwelling unit in a townhouse that extends from foundation to roof and that has a yard or public way on not less than two sides. The general intent of the design of the townhouse is that a townhouse unit could be destroyed without major impact to the adjacent townhouse units. Townhouses can be oriented in different ways and still meet the definition and therefore be built per the IRC. Here's a layout showing the units in a row. You can clearly see a yard or public way is on two sides of each townhouse unit. Here's a real-life example of townhouse units oriented in a row. You can also see that the building does not exceed 3 stories above grade plane. Here's another townhouse building where the townhouse units are oriented in a row, but you'll note that each unit is not fronting the property. This 4-unit townhouse building also meets the IRC as it is 3 stories or less above grade plane, and each townhouse unit is open to a yard on 2 sides. But from an appearance standpoint, it may not look like what you would expect. In this case, these 4 townhouse units are oriented so that the units themselves are located in the 4 corners of the building. Again, this may not be what you expect to see, but each townhouse unit does meet the requirement of the IRC to be open on 2 sides. The general requirement for each townhouse unit is to be structurally independent, but you'll see there's many exceptions. Many of these exceptions are based on provisions allowing for a single rated wall to be shared between townhouse units, referred to as a common wall. Because of this, things such as the common wall itself and its supporting foundation are not required to be structurally independent. You'll also note that exception 6 completely exempts the townhouse units from needing to be structurally independent where protected by an automatic sprinkler system. This is particularly interesting as the model IRC, unamended, already requires an automatic sprinkler system for the building. Now let's start getting into loads. What is a load? The IBC defines what loads are, and when designing the wall bracing system, we'll be particularly focused on the loads that are the forces that result from the weight of the building materials, the occupants, their possessions, and environmental effects. Live loads are defined as those loads produced by the use and occupancy of the building or other structure, and do not include construction or environmental loads such as wind, snow, rain, earthquake, or flood loads, and also does not include dead loads. Whereas dead loads are loads from the weight of the materials of the construction incorporated into the building. Here's some examples. There's a lot of variety in how much materials are used in construction weight, which is why it's important to know that the actual weight must be considered. The IRC requires buildings to be designed to a minimum live loads as outlined in Table R301.5. Design of structural elements for larger live loads is permissible, but will require engineering where such higher loads exceed the prescriptive provisions. While actual weights of materials in construction determines the dead loads, there are maximum allowances for dead loads within the IRC prescriptive provisions, and there are additional dead load limitations for buildings in higher seismic design categories outlined in section R301.2.2.2. Where any of the limitations are exceeded, engineering is required. Live loads and dead loads are also commonly referred to as gravity loads, as they push down on the house. Gravity loads are resisted vertically by joists, beams, columns, bearing walls, and ultimately by the foundation, as it transfers all of that load down to the earth. While not defined by the IRC, environmental loads are forces applied to the structure by environmental factors. Wind, snow, rain, earthquake, floods, essentially Mother Nature. Wind and seismic loads are also commonly referred to as lateral loads, as their force acts on the house laterally. In light gravity loads, all of those loads transfer down through the building and ultimately to the earth. So how do we know what the wind and seismic loads are that must be accounted for? The IRC establishes wind loads in figure R301.2.1.1. This is where you can find out what the ultimate wind speed is for the specific region. Where the figure says, wind design required, the building must be designed in accordance with either the AWC Wood Frame Construction Manual, the ICC Standard for Residential Construction High Wind Regions, ASC Minimum Design Loads and Associate Criteria for Buildings, the ASCE 7, or the International Building Code. Wind design is further classified into categories that are defined by the area around the building as it impacts the magnitude of the wind hitting the building. Exposure B is defined as urban and suburban areas, wooded areas, or other terrain with numerous closely spaced obstructions having the size of a single-family dwelling or larger. Exposure B is assumed unless the site meets the definition of another exposure. Exposure C is defined as open terrain with scattered obstructions, including surface undulations and other irregularities, having heights generally less than 30 feet high, and with that open terrain extending more than 1,500 feet from the building in any direction. But what exposure category would apply to the first buildings in the subdivision, or maybe currently the site would resemble an exposure C, but upon completion of all the buildings, it would be an exposure B? Well, the code addresses that situation by establishing that for a site where multiple structures are to be constructed as a part of a subdivision, the exposure category for a structure shall be based on the site conditions that will exist when all the adjacent structures have been constructed, provided the construction is expected to begin within 1 year. And finally, exposure D is defined as flat, unobstructed areas exposed to wind flowing over open water, smooth mud flats, salt flats, and unbroken ice for a distance of not less than 5,000 feet. Here's an illustration for how wind affects a building. As you can see, as the wind pushes against and passes over the building, it can result in pressure and suction. Some of the reactions that can occur are uplift, overturning, and sliding as the building attempts to resist that load. Now let's look at seismic loads. Seismic loads, like wind loads, are established by a figure in the IRC. Alternatively, the code provides a path to determine the seismic design category based on the site-specific soils and a methodology similar to the IPC. Within the figure, there is also reference of an interactive online tool where you can find the seismic design category for a specific site. To make use of the code easier, the code provides table R301.2, which requires the adopting jurisdiction to fill it out to establish all of the loads that apply in the jurisdiction. Now that we move into the actual application of how those loads will transfer through the building, I want to recognize that there are additional limitations in the IRC for buildings in high seismic design categories. The first limitation is where you have roofs or floors that are not laterally supported and that extend greater than 6 feet away from a braced wall line. This illustrates what that can look like. In this case, there's a roof structure that extends greater than 6 feet away from the building and from the braced wall line. This is not permitted in high seismic design categories, and therefore, in order to do this, engineering is required. Let's see what happens when we apply a load. During a seismic event, as there are no wall bracing for the roof extension, it relies entirely on the main structure to resist the load. As the IRC does not directly address how to resist this unique load, it can result in building failure. The second additional limitation I want to discuss is where the end of a brace wall panel extends greater than 1 foot over an opening in the wall below. Where the opening below does not exceed 8 foot in width and has a certain size header, the brace wall panel may extend further than 1 foot, provided it's not entirely over that opening that's below. Here's an illustration of that limitation. Similarly, because it's outside of the prescriptive provisions, in order to have the brace wall panel extend more than a foot over that opening below, engineering would be required. And here's another illustration. So this location for the brace wall panel would not be permitted, but maybe there's a simple fix. Provided that the brace wall panels are constructed in accordance with the IRC, it could be the fix is just a matter of placing the brace wall panels at a different location, which may not even mean doing anything different other than designated differently on the plans. The location of brace wall panels is addressed in future parts of this series. The third additional limitation is where brace wall lines do not occur in two perpendicular directions. Here is a brace wall line layout where the brace wall lines are not perpendicular. The provisions of the IRC generally have all brace wall lines perpendicular to each other, with very little exception. In cases like this, engineering is required. The fourth additional limitation for high seismic is where you have walls where there are wood brace wall panels and portion of the wall is constructed of masonry or concrete. In this illustration, you can see what that looks like. The brace wall panels shown cannot account for the additional mass and weight of the concrete or masonry that's also a part of that wall. So in a seismic event, it could likely result in a failure. Situations like this require engineering. The fifth additional limitation I want to discuss is hillside light frame construction, where the hillside has a slope that exceeds 1 in 5, and the cripple walls or posts and beams below are greater than 7 foot high, and the total area below is less than 50% living space that has interior wall finishes. And here's an illustration of the hillside limitation. Where the limitation is exceeded, engineering is required. Something I want to point out about this particular provision is that while it discusses post and beam foundations and these limitations regarding slopes and heights of those posts and beams, it's important to understand that per section R602.10.9 of the IRC, that post and beam foundations that support brace wall panels are always required to be engineered. The last additional limitation that I want to discuss is where you have exterior brace wall panels that are out of plane vertically from the foundation below to the utmost story. There's an exception to this limitation that recognizes floor cantilevers, provided the cantilever does not exceed 4 times the depth of the floor joists. The floor joists are 2x10 minimum, spaced no more than 16 inches on center. There's a backspan of greater than 2 to 1. The floor joists at the end of the brace wall panels are doubled, and gravity load carried by the end of the cantilever joists are limited to uniform wall and roof loads in reactions from headers having a span that is less than or equal to 8 feet. This shows what that can look like. In the case where you do have 2x10s that are 16 inches on center and max, and D does not exceed 4 times the depth of the floor joist, then it would be permitted. Otherwise, engineering is required. This is an interesting real-life scenario showing a cantilever. In this case, the gravity loads are being transferred out to a beam closest to us and into a column that's headed down to a foundation. So while the gravity load in this scenario is not actually a cantilever function, the limitation we discuss is based on seismic, meaning lateral loads. So for that case, this is a cantilevered situation where the brace wall panels above do not align vertically with the wall below and down on the foundation. Therefore, this would need to be evaluated to determine whether or not it's within the limitations. We've discussed several times about situations where you step outside of the prescriptive provisions, and I said that engineering would be required. More specifically, this is outlined in section R301.1.3 and recognizes that when you have these situations that exceed those provisions, that the extending engineering is to address those non-conventional elements so that it's compatible with the performance of the conventional frame system. It does not mean that the entire building needs to be engineered, rather just as what's necessary to address that specific situation. Another path for compliance when exceeding limitations are listed in the IRC. Where exceeding the wind limitations, you can utilize design for the ACE 7, the ICC 600, or AWC's wood frame construction manual for 1 and 2 family dwellings. Where exceeding the seismic design limitations, it's permissible to design in accordance with the IBC or AWC's wood frame construction manual for 1 and 2 family dwellings. AWC's wood frame construction manual for 1 and 2 family dwellings, as referenced in the IRC, are available on AWC's website, www.awc.org. Now let's discuss some basic bracing concepts. In this illustration, you can see a stud frame wall, and under lateral load would have a tendency to rack. To prevent the racking, the wall needs to be braced. Diagonal tension ties create a triangular geometry. Compression ties are rarely effective, if at all. Diagonal board sheathing, however, works in this mode, also lead-in wall brace method. It's also important to recognize that when applying the braces, that ultimately everything relies on the fasteners. Here in this illustration, you can see how the force is pushing and pulling on the individual fasteners as it resists the load. This shows an individual fastener as the load is transferred. As you can see, the fastener has to be able to resist the shear and withdrawal that occurs when this load is applied. This shows the importance of properly installing fasteners. If a fastener is overdriven, it reduces the strength of the connection because there is less wood in contact with the fastener. Here are some real-life scenarios. Can you see all the fasteners? Even on the main floor, it may be difficult to determine compliance, but it's particularly harder for a second or third story. Ultimately, it requires the installer to assure proper installation of the fasteners, and the building department to determine their inspection procedures. But the code must be met regardless. Using the correct type of fastener is also very critical. Table R602.3 paren 1 of the IRC provides prescriptive fastening schedule and lists out the fasteners therefore. When applying this table or any other provision in the IRC where fasteners are listed, it's important to rely on the length and diameter specified for the fastener.
Let's practice tracing loads. In this illustration, you can see how gravity loads such as dead load and roof snow load transfers through the bearing elements. The load on the roof is carried by the bearing wall to the foundation. Where there are openings such as windows and doors, that load is first transferred to the headers and then out to the jack studs on each side of the opening. As the load has been gathered up and transferred to the jack studs, the magnitude of the load at those points where it transfers to the foundation is much greater than the dispersed loads in the adjacent walls. These higher magnitude loads are referred to as point loads. When the header tables require multiple laminations, for example 2 2x8s, it's important that the laminations are nailed together per table R602.3 paren 1. If it isn't, then the interior side lamination will take the force first, making it subject to failure. You can see this more clearly by these lines showing how the floor joist bearing on the header starts to deflect. Its weight will impact one of the laminations first. Proper nailing ensures the laminations act as one. When a header is required over adjacent openings, it's important that it is constructed so that each member is oriented as a single span, meaning that each individually has code-prescribed bearing and it does not run continuously across more than one opening. This is because members spanning multiple openings will experience a great amount of compression at the mid-support, which can cause the members to buckle. It's important to understand that only single spans are accounted for by the prescriptive tables, so any multi-span headers require engineering. Here's something you may have seen that is not allowed by the prescriptive code. By not splicing the header at the support, the members are not acting as single spans. Additionally, if each lamination is required by the tables, then some of the laminations do not have the code-prescribed bearing. This type of splicing requires specific engineering to demonstrate how to properly fashion laminations together and analysis to assure that all the loads are resisted as a single multi-span header. Earlier, we traced gravity loads that were gathered up by the header and transferred through the jack studs. This resulting point load needs special attention as we transfer it to the foundation. Here you can see what occurs at the rim joist of the floor system. While the rim board is sufficient to transfer the distributed loads from the adjacent space studs, a larger point load can be too much for the compression strength of the rim board to handle. To prevent compression at the point load, blocking needs to be added in alignment with the jack studs. It's good to keep in mind that wood has better compressive strength parallel to the wood grain, so the wood grain of the blocking should be oriented vertically.
Section R 602.3.3 addresses transferring grappling loads from trusses, joists, or rafters to the studs below by requiring them to align with certain tolerances. Generally, where the studs below are 24 inch on center and the joists or rafters are spaced greater than 16 inch on center, they must align within 5 inches. Also, if there is only a single top plate, they must always align within 1 inch tolerance. In the picture shown, the 5 inch tolerance is exceeded, but because the top plate consists of two 2x6s, it meets exception number 1. Note that these tolerances are only for distributed loads, and any point loads from beams or girder trusses would need to be supported by a sufficient column or stud back. Now that we've looked at transferring gravity loads, we will now look at transferring lateral loads. In this illustration, the load from the wind is pushing against the building from left to right. You can see the loads are resisted by transferring along the top plate to the brace wall panels. Presuming the brace wall panels are constructed properly, they prevent the racking of the wall. The brace wall panels then need to be able to resist overturn. As you can see, the load within the panel as it resists the overturning forces means there is a point load acting downward on the right side of the panels, and an uplift load on the left side of the panels. As we look at the code provisions for wall bracing in other parts of this series, this will help us better understand the code provisions. You can also see that ultimately all the loads, like gravity loads, are transferred to the ground. Another way to visualize how lateral loads are transferred would be to turn the building sideways and think about them like a gravity load, the building hanging on a cliff. In the last illustration, we presumed that the brace wall panels were constructed properly to prevent racking. A critical part of that is having horizontal joints within the panels properly blocked. Otherwise, as shown here, racking may still occur. Blocking also requires sufficient nailing to transfer the load to the blocking and make the sections on each side of the joint act as one. Here's an example of blocked horizontal joints. In other parts of this series, we'll discuss why horizontal blocking is critical, but only required for brace wall panels. The IRC provides figures 602.10.8 paren 1 and 2
to require proper connections of brace wall panels to the structure above and below them. This assures that the loads are transferred ultimately to the ground. On the left, it shows proper nailing of an exterior brace wall panel and an interior brace wall panel with joists above and below that are perpendicular to the brace wall panel. This requires blocking between the joists. On the right, you can see two options for connections of interior brace wall panels that are parallel to the joists above and below. In that scenario, either a joist must be located in alignment with the brace wall panel, or blocking must be provided 16-inch on center to transfer the load to the parallel joists. In this picture, we can see what blocking of joists may look like if required due to alignment with an interior brace wall panel. Note that similar to horizontal blocking in the brace wall panels, the blocking we just discussed in the IRC figures are only required where there is an interior brace wall panel, but there may be blocking required for other reasons, such as at bearing supports of the joists.
Once the load reaches the foundation, the connection between the wood framing and the foundation must be provided. Generally, the code requires this to be achieved by providing anchor bolts that are spaced no more than 6 foot on center and are embedded 7 inches minimum into the concrete. Like many provisions for resisting lateral loads, the code has more stringent requirements for buildings in higher seismic design categories, so it's important to look for such requirements. Also, as we look at the brace wall provisions in the rest of this series, there may be situations where hold downs are also needed to resist uplift loads. This picture shows anchor bolts with plate washers. On the right side, you can see concrete dust around the bolt that indicates that it was installed after the concrete was cured. Post-installed anchors are only permitted as an alternative method and must be equivalent to the performance as the code prescribes 7-inch embedded anchors and installed properly. While not written in the IRC, due to difficulty in proper inspection, the approval of such an alternative method may also require special inspection, such as required by Chapter 17 of the IBC. A common situation for buildings is where the first floor's framing does not bear directly on the foundation, but rather on a wall that is not full height to account for a level below that is partially below grade or for stepped foundations. Such walls are referred to as cripple walls. In order to transfer the loads from the brace wall panels above, the general rule is that cripple walls must be braced using the same method as a wall above, but also have a total length of bracing that is at least 115% of the required length for the brace wall line above. The code provides an option to address the transferring of the loads through the cripple walls that are less than 48 inches in height by treating the cripple wall as a story. By doing this, they meet the IRC provisions as the first story, and therefore the story above becomes a second story above grade plane. In cases where any cripple wall section exceeds 48 inches in height, the code no longer makes it an option, but rather requires the cripple walls to be counted as a story. This is important to understand as it may impact the ability to provide wall bracing for the building using the prescriptive provisions where there are 3 stories above the cripple walls. Here's an example of why redesignating the cripple walls as a story can be an issue. In the picture, the cripple walls exceed 48 inches, therefore they must be treated as a story. As you can see, this would mean that the top story would become the 4th story, noting that the top story is not enclosed by the roof structure, therefore it would not be exempt from being a story per the habitable attic provisions. The prescriptive provisions of the IRC do not provide for a 4th story above grade plane, therefore engineering would be required. Section R 602.10.9 provides other specific situations that must be accounted for when transferring the brace wall panel loads to the ground. It recognizes all post and pier foundations must be engineered. Masonry stem walls that are less than 48 inches long must have specific reinforcement per figure R602.10.9. Concrete stem walls that are less than 6 inches thick, taller than 12 inches, and less than 48 inches in length must also have the reinforcement per the figure. These reinforcement requirements are in addition to what is required per the foundation provisions in Chapter 4 of the IRC. R602.10.9 also allows the support of brace wall panels to be by cantilever floors in accordance with Section R502.3.3. This is not to be confused with the limitations for cantilevers in high seismic design categories that we discussed earlier, but rather the cantilever floor provisions referenced herein are the general requirements for cantilever floors. So while meeting this cantilever floor criteria is permissible for support of brace wall panels in general, if in a high seismic area, it must also meet those previously discussed limitations. So what happens if the building isn't properly connected to the foundation? Here you can see one possible failure by sliding. While clearly a concern in seismic events, there are real-life examples of buildings that moved as a whole off of the foundation due to wind events. Here's a real-life example of a building built on a post and pier foundation. Think about how loads are transferred as we look at the underside of the building. How can we be sure that loads will transfer to the ground? There are no prescriptive provisions for this type of construction, so engineering is always required. Remember when we discussed limitations for hillside construction? Regardless of the slope of the hill or the height of the posts, you now know the code always requires engineering for posts and piers supporting brace wall panels. Without proper engineering, there is no way to know the loads will be resisted and the building is subject to failure. When looking at the roof, it's important to recognize that if the roof is not properly connected to the brace wall panels, then the loads won't be transferred and failure can occur at the roof portion of the building. The code provides several options. The first is where the heel of the roof is less than 15¼ inches above the top plate. In that case, the load may be transferred through solid blocking that is properly nailed. While the blocking we just discussed is only required at brace wall panels, there is a general requirement for blocking the roof members where they have a depth to thickness ratio exceeding 5:1 based on nominal dimensions. This would mean that if they are greater than 2x10, then blocking is required regardless of the location of brace wall panels in order to prevent rotation of the framing. In these pictures, the blocking may not have been required for rotation of the members, but as the panels below have horizontal blocking, it is likely that they are brace wall panels and therefore blocking between the trusses is required above them. Another option provided is where the heel is up to 4 feet high, the blocking may be located out at the end of the soffit, and then the load is transferred through the soffit back to the wall. As noted in the figure, this requires that the soffit be constructed in the same manner as required for a brace wall panel, such as the panel thickness and proper nailing. This picture shows a tall heel. While the soffit may not be constructed at the time of the framing inspection, if that option is used, it must be done correctly and is subject to inspection. The third option is also where the heel is up to 4 feet high. The heel itself may be braced by providing a panel meeting the brace wall panel requirements between the trusses. You'll note that in the figure, it requires 2 bind blocking on top of the top plate and at the top of the heel to allow for proper nailing of the panel. This heel exceeds 4 feet, and the panel section is not blocked at the top or bottom or at its horizontal joint.
In order to assure that the loads are properly transferred to the brace wall panel below, engineering is required. It is possible that the engineering for this purpose can be included as part of the engineering for the entire truss system. Section R802.10.3 requires trusses to be braced to prevent rotation and for lateral stability, per the truss design. In absence of specific bracing requirements, the Building Component Safety Information Guide, published by the Structural Building Components Association, applies. Another load to consider is uplift from wind. The code requires connections to resist uplift, which must be capable of resisting the uplift loads as determined in Table R802.11 or determined by engineering, which may be from the truss design documents. Where the uplift force does not exceed 200 pounds and the rafters are spaced no more than 24 inch on center, the connection is permitted to be achieved by prescriptive nailing per Table R602.3 per N1 only. Here's Table R802.11. As you can see, depending on the roof pitch and span, rafter spacing, and the wind speed, there are many scenarios where the uplift would not exceed 200 pounds. As mentioned in the last slide, in those cases, nailing per Table R602.3 per N1 is sufficient, and no additional connector would be required. The second criteria given that allows for prescriptive nailing only is where the basic wind speed does not exceed 115 miles per hour, the wind exposure category is B, roof pitch is greater than or equal to 512, and the roof span is less than or equal to 32 feet, and the rafters are spaced not more than 24 inches on center. If you apply this criteria to the uplift table we just looked at, you'll notice that the resulting uplift for this criteria does not exceed 200 pounds. And what happens if we don't properly connect the roof to the wall framing? As the wind generates uplift, the roof structure can be removed from the rest of the structure. Not only is this going to be a bad day for the owner, but once the roof is removed, it can no longer act as a diaphragm, transferring loads to the brace wall panels, which will lead to further damage to the rest of the building. Like all other loads, uplift loads must also be transferred to the ground. Also, per the wall bracing section R602.10.2.1, if uplift is not accounted for per R602.3.5, then the prescriptive wall bracing provisions cannot be applied. Similar to the roof-to-wall connection in R602.3.5, it provides criteria for when it is sufficient to rely on the prescriptive nailing of Table R602.3 per N1 only. Also, similarly, you'll see it includes the option for where the wind speed is less than or equal to 115 miles per hour, exposure category is B, roof pitch is greater than or equal to 512, and the roof span is 32 feet or less. It also allows for where the uplift at the top of the wall is less than 100 pounds per linear foot, which conveniently is equal to 200 pounds that's 24 inch on center. It also recognizes that where there is a full height wall section above the location in question, that the values from R802.11 may be reduced by 60 pounds per linear foot when making that determination. Where the uplift at the top of the wall does not exceed 100 pounds per linear foot, you cannot rely on the prescriptive nailing alone, and rather, an approved connector must be provided that can resist the load at the location in question. As discussed, when determining what the uplift load is by using section R802.11, the uplift is reduced by 60 pounds per linear foot for each full height wall above the location in question. The final option given for resisting uplift is to utilize wall sheathing and fasteners designed to resist combined uplift and shear forces in accordance with accepted engineering practice. And if the uplift loads aren't fully transferred to the ground, this, could be you.